Hi, this is Alex from devstories.eu. Python Cheminformatics and AI, Episode 9 of 22. A complex 3D virtual screening script used to require hundreds of lines of fragile code. You had to manually generate conformers, handle failures, compute multiple descriptors, and stitch the arrays together before even touching a model. Now, you can architect the entire process in a single elegant pipeline definition using end-to-end ML pipelines. In machine learning, a pipeline is a sequence of data processing steps and a final estimator grouped into a single object. In cheminformatics, especially with 3D structural data, pre-processing is notoriously fragmented. You take raw SMILS strings, calculate 3D coordinates, run force field optimizations, extract features, fix missing values, and finally train a classifier. Doing this manually means writing custom loops and intermediate data structures that break easily and leak memory. We will walk through building a complete scikit-learn pipeline that takes raw SMILS strings straight to a random forest classifier. The first step in the sequence is conformer generation. You initialize a conformer generator and pass it as the first stage of the pipeline. It reads the 2D input and computes the 3D structures. You can configure it to optimize the geometry using a force field like MMFF94. It automatically parallelizes this heavy lifting across all available CPU cores. Now, the second piece of this is feature extraction. For 3D tasks, combining different geometry descriptors captures more molecular information. You use a scikit-learn feature union to compute the getaway and whim fingerprints simultaneously. Both of these fingerprint classes act as stateless transformers in the pipeline. They take the 3D conformers from the previous step, calculate their respective descriptors in parallel, and concatenate the results into a single wide feature matrix. Next, you must handle computation failures. 3D descriptor algorithms sometimes fail to process highly complex or strained molecules, resulting in missing values in your matrix. The pipeline handles this without custom error handling. You drop a simple imputer directly after the feature union. If a getaway or whim calculation outputs a missing value, the imputer catches it and replaces it with the mean of that feature across your dataset. Finally, you cap the pipeline with your predictive model, which in this case is a random forest classifier. To architect this in code, you call the makePipeline function. Inside that function call, you pass your conformer generator. Next, you pass the feature union containing your getaway and whim fingerprints. Then comes the simple imputer, and lastly, the random forest classifier. You assign this entire sequence to a single variable. When you call the fit method on that pipeline variable, you pass your raw training SMILS strings and your target labels. The strings flow sequentially through the conformer generator, into the feature union for fingerprinting, through the imputer to clean the data, and straight into the classifier for training. When it's time to evaluate, calling the predict method on your test SMILS strings forces the new data to follow the exact same path. Here is the key insight. State and data routing are managed entirely by the pipeline object, meaning you never hold intermediate dense arrays in memory or write custom data loaders for your conformers. That's all for this one. Thanks for listening and keep building.